So today I'm a little bit tired, so I think I'm gonna just watch videos about these topics here because I have to study them anyway. So I think it would be a good idea to study videos, to watch videos, not study videos. These ones I did yesterday off stream. Has attribute is pretty much a way to return true or false if a class has an attribute. And if the attribute is false, it doesn't matter because as long as the class has the attribute, it's gonna return true. And if the class doesn't have, it returns false. Utils, I didn't understand really well what it is, but it seems to be a way for people to build the most useful, put the most useful functions of a project, the ones that come up very frequently. So it's kind of like a standard library, from what I understood. Oh, let me search for these topics. And I think I'm gonna try to finish the other day the stuff. The stuff that I was doing with the graphics. I tried to download to save the Tensorflow graph, but the Tensorflow graph was too big, so we couldn't save. So I was doing a quick search to see if I can increase the size of the graph or change the configurations, and I think it might be worth it to play around with that later. And maybe try to also learn the other graph style, which is network something. Vis.js network. Try to integrate both after I run that script, and also try to change some things on that script that so that it's not only searches for modules but create variations of that searches for classes. Because the main point is to study the libraries to create artificial intelligence thing and networks. This is the TensorFlow graph. It's absurdly insane. And because it's so big, I imagine that it corrupts the file when I try to download it in PNG format. It's crazy how much thing there exists here. And I'm probably not sure if I have to study all of them to understand. Probably not. But if I manage to save this on PNG format, it's gonna be really good because obviously it's a lot better to study when you know the graph of connections. And then maybe I can build these graphs for the smaller files as well, like I was doing on the other script. And that way that it might be there might be a chance that some of the graphs are gonna be more simple. And I can start with those and see how they fit on the overall picture of the thing. So yeah, another thing that I have to study is obviously the sys thing. I'm gonna study that a lot, I think. Because it's the most important library in Python, apparently, from a behind the scenes perspective, let's say. Maybe there aren't videos about this, but if there aren't, I'm gonna research on Stack Overflow probably or documentation. Inner. Oh yeah, I think I'm gonna spend around 2 hours here only today. But maybe I'll spend more.
In this
Who knows?
video, the property, built-in function, and decorator in Python 3. Let's start with a look at the docs. The main thing I want to highlight here is there's actually two completely different design patterns for using the property function. The first one is the one you see here, and the second one is just below here. And it importantly states that here that this code example above is equivalent to the first example. So basically, there's two patterns for using the property function. Now, let's start with the basics. I do have examples here for each of the two design patterns from the docs, but I want to start with something simpler just to make the whole concept clear. So you know that when you create classes, you can just assign attributes to them, and it'll come out like this, right? Pretty normal. We can create a car class and then assign the name Joey, and then boom, we have a car named Joey. Cool. But these getter, setter, deleter attributes within a car class kind of get tricky to do in one-liners like this. So what if you want to do a conditional, right? So you'll name the car Joey if true, else we'll name it, I don't know, Dave. Like it's going to start getting complicated. So what these do, what the property attribute does, is it just makes it way easier to deal with setting attributes, deleting attributes, creating attributes. And to me, what's important is how it helps with validation. All right, now let's talk about the two methods for using the property decorator or the property function. I'll tell you straight up that I prefer using the decorator. I think it's a better way to do it. It just looks way more clean. And although it's actually somehow one line of code more, this is 18 and this is 17, in this method, you have to create your functions first, and then you assign those functions to the attribute or whatever it's called. I just don't like how you do the functions first, and then we finally create the name at the very end. I'd much rather just create the name at the beginning and get started. So let's do that. In this example, I did instantiate a car. I set its name to be Jimmy, and then I want to change the name to Joey. And when we first print it out, and then when we change it, you're going to see these print statements getting hit. So let's run this. Cool. So here we can see that we're immediately in the getter when we do the print, and then we're in the setter when we set the name to Joey, and then we're in the getter again when we print it again. And so what's cool about this is, let's say we wanted to add some validation. So let's say we wanted the car name to have to be, I don't know, at least 7 characters. So we could say if len greater than 6, then we'll set the name, okay? So Joey's not, so what happens? Well, it's still Jimmy because it didn't pass the validation. But if we change it to something longer, like, I don't know, Stephanie, when we run this, it'll successfully change. So when you start doing a lot more validation with your classes, when you start having validation around your attributes, that's when this property decorator is going to come in handy. And it's just way easier to do it than in this old-fashioned way, right? Cool. So that's the first way of doing it. So here again, I did create those print statements so we can run this exact same thing again, see how it works. You can see that when it gets printed for the first time, we're calling the get, and then when we want to rename the car, the set name function is called, and then the get name function is called in that second print statement. So happening the exact same way as in our first design pattern, it's completely equivalent. Now, like I said, using the decorator is my preferred method of doing it, but you can do it however you want. Basically, the property function is just a better way of organizing your code and doing more complicated validation within your classes. Thanks for watching.
Not sure. I'm not sure.
Strange, but the name attributes getter, setter, and deleter functionality like you may have seen in some other languages. So if you've been following along with my object-oriented video so far, you may have noticed that I stripped down the employee class here a bit, and that's just so we can focus on these attributes without the other code getting in the way. Okay, so far with our employee class, some of you may have noticed that our email attribute depends on our first name and our last name. So when we create our employee object here, it comes into our init method, and it sets the first name, the last name, then it sets the email to our first name dot last name at email.com. And also we have this full name method down here, which prints out the current first name and last name together. So if I go down here and create this simple employee object and then print out the first name, email, and full name, you can see that all of these are what we would expect. So the first name is John, the email is johnsmith@email.com, and the full name is both of those together. So let's go here and now let's set our employee.firstname, and I'm just gonna set that first name equal to Jim and rerun this. So you can see down here that the first name was changed to Jim, but the email still has our old first name. Now, the full name method here doesn't have this problem because every time we run the full name method, it comes in here and grabs the current first name and last name. So what if the people who are using our class said that we need to fix this? So they don't want to change the email every time they change the first name or the last name. So they want us to make it to where it updates the email automatically when either the first name or the last name is changed. Now, your first thought there might be to just create an email method just like we did here with our full name, but the problem with that is that it will break the code for everyone currently using the class. So they would have to go through and change every instance of the email attribute with an email method. Now, this is usually where people from other languages like Java will bring up the benefits of getter and setter methods. And it's a good point because this is where getter and setters really come in handy. But we have the ability to do this within Python using the property decorator. Now, the property decorator allows us to define a method, but we can access it like an attribute. So for example, let's go ahead and pull this email attribute out into a method similar to our full name method. So I'm actually just going to copy the full name method here and paste this in, and I'm going to call this email. But instead of printing this out like the first name, I'm going to print this out like our email would show up. So the first name dot last name at email.com. And so now I'm just going to come up here and remove our email attribute and save that. So right now our email method is similar to our full name method. So each time we ran it, it would get the current first name and last name, but we'd also have to go through and change our code to where every email attribute is a method call. So for example, where I'm printing this out down here, I would instead have to go down here and add parentheses to this .email. And so now if I run this here, you can see that this solved our problem where it set our email address to the new first name, but this also means that anyone using our class would have to change their code also. So that's not what we want. So let's go ahead and take these parentheses back off. So in order to continue accessing email like an attribute, I can just add a property decorator above this method. So I'm going to go ahead and add this one. So this is just at property. And just by making that small change, now if I run our code, then you can see that that works. So we're defining our email in our class like it's a method, but we're able to access it like an attribute. And we can do this just as easily with full name as well. So if I was to add this property decorator onto full name and then take off these parentheses there and run that, then you can see that that works also. Now I know that goes against what I said about changing the code, but this is just an example. And I also wanted to use the full name to show you an example of how you can use a setter. So let's say, for example, that we wanted the ability to say employee1.fullname and set it equal to, let's just say Corey Schaefer. And let's say that by setting this full name, that we also wanted it to change our first name, our last name, and our email. And right now we can't do this. So if we only have the full name with the property decorator, and I try to set this like this, if I run this here, you can see that we get an error there. And if we look at the error, it says that we can't set the attribute. Okay, so for now, I'm just going to comment this out and rerun that. So in order to do what we were trying to do there, we're going to have to use a setter, and that's going to be another decorator. Now, this might look a little strange, but the name that we're going to use for our setter is going to be the name of the property. So in this case, it's going to be full name. So I'm going to say at full name dot setter. And then underneath this decorator, we just need to create another method with the same name. So this is going to be a method with full name. And this is going to take in self, and I'm going to call this name. Now, this name value here is the value that we are trying to set. So in this case down here, it would be this full name here. So I'm going to come in here, and we want to set the first name and the last name using this full name here. So what we can do is we can just split that name that we passed in on the space separator. So I'll say first, last is equal to name.split. We'll split on that space. So that's going to split that name into two parts. And the first part before the space will be the first name, and the second part after the space will be the last name. So now we want to set our employee's first name and last
The
name.
only question I still have is why would you use this? Because, well, what's the point? Maybe I should ask this question to the gods of the internet. Why? What is the point of using property in Python? When is it useful? It's actually pretty amazing that we can we live in an age that we can type anything on the internet and get an answer to. I think oftentimes we get for granted how powerful this is. It's really insane.
Equal to those values. So I can just say self.first is equal to first, and self.last.
Like everything I learned so far over the last year, starting from nothing to code, is pretty much free from the internet, and I didn't have to pay anything, which is absolutely insane.
Is equal to last. So now that I have that setter, if I come down here and uncomment out this line that gave us an error before and rerun that, then you can see that that works. So what happened here is that whenever we set this full name equal to this name, it came into our setter here and it parsed the names from that value that we set, and then it set.
Not everything I paid for our site, but it wasn't really. Was just I just learned about the neural network part, and everything that I learned there I could have learned it for free.
Our first name and last name. And since we set the first name and last name, even when we printed out our email, it came in here and grabbed those correct values. Now you can also make a deleter in the same way. So let's say that if I was to delete the full name of our employee, that I wanted it to run some kind of cleanup code. So to do this, I'm just going to copy our setter here and paste this in below. But instead of a setter, this is going to be a deleter for full name. It's deleter. And this won't be accepting any other values other than self. And I'll just go ahead and remove these here. And just so that we can see this doing something within here, I'm just going to say delete name. And I'm also just going to do a self.first is equal to none and a self.last is equal to none. So the deleter code there is what gets run whenever we delete an attribute. So at the very bottom here, if I do a delete of employee1.fullname and run that, then you can see here that it came in and ran that print statement that was in our deleter. It also set our first name and last name equal to none values. Okay, so I think that's going to do it for this video. I hope you got some ideas for how you can use the property decorator within your classes. Now, this is a nice feature because it allows us to access attributes without putting getters and setters everywhere. But if we need that functionality, then it's easy to add in with the property decorator. And if you do this correctly, then people using our class won't even need to change any of their code because they'll still be able to access those attributes in the same way that they did before. Now, that wasn't exactly the case in our example here because I changed the full name method into an attribute, but I only did that because I wanted to show how we could use the full name as a setter to change the first name and the last name. So you will want to be careful with changes like that if other people are already using your classes.
So I'm probably gonna forget this at some point, but at least now it's on the back of my mind. Whenever I see this, there's a slight chance that I will recognize and understand what it is. But I wish people, when they were Obviously, this is a very good tutorial. This guy is really good at explaining stuff. But I wish they would put it into context of when it is actually like he tries to do that, but yeah, I guess it's just hard to find an actual application that has the thing to show it. But I wish they did that, because then it would be much better to understand it. Because it's not only what it does, is what's the moment you decide to do it. That's the issue I'm having whenever I code on my own, because usually I just default to the stuff that I know. And it's really hard to decide when to use something new. And I think that's the challenge of trying to incorporate this stuff into my code. Because everything that these things do, it seems like you could do in a different way that is just more simple. So I always try to think about what was the moment that someone come up with this thing to incorporate in the language, and why did they do it. Property Decorator in Python. Its use cases, advantages, and syntax. Start value. Why would you use properties in Python? You may consider a Pythonic way of working with attributes because the syntax used to define properties is very concise and readable. You can access instance attributes exactly as if they were public attributes while using the magic of intermediaries, getters, and setters. Yet can access instance attributes exactly as if they were public attributes. Validate new values and to avoid accessing or modifying the data directly. By using at property, you can reuse the name of a property to avoid creating new names for the getters and setters and deleters. These advantages make properties a really awesome tool to help you write and more concise and readable code. Let's switch to decorators. The decorator function is basically a function that adds new functionality to a function that is passed as an argument. Using decorator functions like adding chocolate sprinkles to an ice cream. Lets us add new functionality to an existing function without modifying it. A function that adds a new functionality to a function that is passed as argument. In the example below, you can see what a typical decorator function looks like in Python. New function is add decorator initial function. Let's analyze these elements in detail. You first find the decorator function def decorator f sprinkles that takes a function f as an argument. So it's gonna take this function as an argument here. This decorator function has an nested function, new function. Notice how f is called inside new function to achieve the same functionality while adding new functionality before the function call. Inside, oh, so it's called here. You could also add new functionality after the function call. The decorator function itself returns the nested function new function. Then below we find, oh, that's why it's called a wrapper. So it's pretty much just taking that add method of decorators just creates these functions that has a new function inside it, takes the function that is wrapping as an argument, and then adds extra functionality to the function, and then calls the function at the end and returns the new function. Initial decorator, if we run the code, we see this output. That's how the decorator function runs, even if we are only calling initial function. This is the magic of adding add decorator. Note, in general, we would write add decorator function name, replacing the name of the decorator function after the the symbol. I know you may be asking how is this related to the property. The property is a built-in decorator for the property function in Python. It is used to give special functionality to certain methods to make them act as getters, setters, or deleters when defined properties in a class. Now that you are familiar with decorators, let's see a real scenario of the use of property. So, when to use getters and setters in Python? Let's say that this class is part of your program. You're modeling a house with a house class. At the moment, the class only has a price instance attribute defined. This instance attribute is public because its name doesn't have a leading underscore. Since the attribute is currently publicly, it is very likely that you and other developers in your team access it and modify the attribute directly in other parts of the program using dot notation like this. So a question that popped up in my mind is if has attribute gives true, returns true to private attributes. And I think it does because, like I read some other time, private attributes are not really private. They're just used as you just use the underscore before as a convention and not something that is specific from the language. But I think it is worth searching. I don't think it's gonna. I think it returns true. Maybe I can create a class here real quick and check it out. Class, okay. I keep forgetting that self is this, but so B goes there. So this is not how it's used. And I should put the underscore here. B is like this. Oh. Also, the thing is inside. I need some brackets. There we go. Yeah, so it returns true. It's probably because Python doesn't care if it's not really private. It's just convention. This instance attribute is public because its name doesn't have a leading underscore. Since it is attributed publicly, the object represents a variable that references an instance of else. So far, everything is working great, right? But let's say that you're asked to make this attribute protected, non-public, and validate a new value before assigning it. Specifically, you need to check if the value is a positive float. How would you do that? Let's see. Changing your code at this point, if decide to add getters and setters, you and your team will probably panic. This is because each line of code that accesses or modifies the value of the attribute will have to be modified to call the getter or setter respectively, otherwise the code will break. Change from the object price, change from object price. But properties come to the rescue. With at property, you and your team will not need to modify any of those lines because you'll be able to add getters and setters behind the scenes without affecting the syntax that you use to access or modify the attribute when it was published. Awesome, right? Add property, syntax, and logic. If you decide to use add property, your class will look like the example below. So add property, then price here, price setter. If new price and instance new price floats off. Price. Specifically, you can define three methods for a property: a getter, a setter, and a deleter. Access attribute, access value of the attribute. Sets the value, and deletes the value. Means price is now protected. Please note that the price attribute is now considered protected because we added a leading underscore to its name in self._price. In Python, by convention, when you add a leading underscore to a name, you're telling other developers that it should not be accessed or modified directly outside of the class. It should only be accessed through intermediaries, getters and setters, if they are available. Getter, how we have the getter method. Here we have the getter method, the getter method. Getter method returns the self price. Notice the syntax property used to indicate that we are going to define a property. Notice how this immediately improves readability because we clearly see the purpose of this method. Def price self, the header. Notice how the getter is named exactly like the property that we are defining, price. This is the name that we use to access and modify the attribute outside of the class. The method only takes one form of parameter self, which is a reference to the instance. This line is exactly what you would expect in a regular getter. The value of the protected attribute is returned. Here's an example of the use of the getter method. Create instance access value. Notice how we access the price attribute as if it were a public attribute. We are not changing the syntax at all, but we are actually using the getter as an intermediary to avoid accessing the data directly. Setter, now we have the setter method. Notice the syntax at price.setter used to indicate that this is the setter method for the price property. Notice that we are not using at property.setter, we are using price.setter. The name of the property is included before .setter. Def price, self new price, the header and the list of parameters. Notice how the name of the property is used as the name of the setter. We also have a second form of parameter new price, which is the new value that will be assigned to the price attribute if it is valid. Finally, we have the body of the setter where we validate the argument to check if it is a positive float, and then if the argument is valid, we update the value of the attribute. If the value is not valid, the descriptive message is printed. You can choose how to handle invalid values according to the needs of your program. So this brings another question: if these names are just by convention, or you can do pretty much anything. Like this, is the property function some function from the library itself? Probably is, or when you use this, you're just wrapping this function here with the other function there, with the init method for the price. I'm not really sure if it is convention or not. Have the body of the setter where we validate the argument, check if it is a positive float, and then if the argument is valid, we update the value of the attribute. If the value is not valid, a descriptive message is printed. This is an example of the setter method at property. Was blah blah blah. Deleter, Same thing. Don't necessarily have to define all three methods for every property. You can define read-only properties by only including a getter method. You also choose to define a getter and setter without a deleter. If you think that an attribute should only be set when the instance is created, or that it should only be modified internally within the class, you can omit the setter. You can choose which methods to include depending on the context that you are working with. Yeah, it is a property function. I think she mentioned that there. Special descriptor object. So another keyword to search her. I already forgot. Oh, class method is when you want to make a method be accessible just like the class. You want to make a method act like the class, something like that. It takes the class as an argument. The access decorator should they return a new property object. This is a copy of the old object with one of the functions replaced. Remember that the decorator syntax is just syntactic sugar. Syntax really means this the same thing as def soft because property full. So this creates the object of the property class. The full the function is replaced by property full, which we saw above is a special object. Then when you see full.setter, what you're doing is call the properties.setter method I showed you above, which returns a new copy of the property, but this time with the setter function replaced with the decorator method. Following sequence also creates a full property, blends the decorator methods first create property. So set and delete are dunder methods. Okay. Watch one
Hey guys,
more
I'm back with a new
video.
video. In this video, we'll learn about getters and setters in Python. Now, the concept of getters and setters in Python is not the same as in other programming languages. The reason for programmers to define private variables in Python are not hidden by data and class fields. Salary and age set that to age, self.salary set that to salary, and self.company name set that to company name. Now we can make use of the property decorator in order to create getter. Now let us define a getter for getting the name. I want to define a setter, so I can say at it is a setter for our company name. So now let us define the name of the developer, which is Alex. Age is 20 for developer instance, so I can say print. And now let us run the file. So Python getters setters.py, and you can see we are getting SpectroCoin logged to the terminal company, and we are passing on the new company name, which is Google. So if we now print the company name by saying developer object.company and run the file, you can see that we are now getting Google. So this was a very short video available.
Nice.
Descriptors provide a powerful general-purpose way
I think I'm also gonna review the class method.
In my experience, they are often taught poorly as simply the mechanism that's behind properties in a hand-wavy fashion and then ignored once you have the basics. I'm going to show you that they're simple to understand and that you will subsequently have access to a larger coding toolset and you will have a deeper understanding of how Python works. I'm going to present a concise but accurate and thorough explanation and demonstration of the descriptor protocol, including the use of properties that will make you a better programmer and better able to understand large code bases on GitHub. We're going to cover Python's automatic name mangling, what the descriptor protocol is, how to write in CPython is written in C. We have an attribute, dunder secret value, and we'll just assign the value of 1 to it. We'll create an instance, instance A. We can see the repr for instance A, and there's nothing untoward about it. However, when we use the dot notation and try to access the value of dunder secret value, we get an attribute error. How about trying to access it directly from the class? Again, attribute error. Let's use dir just to see what we've got available to us. As you can see, the first entry in this list is _a, the class name, and then dunder secret value. This is what Python name mangling is. Whatever attribute you have, if it starts with 2 underscores, then Python is going to prefix your attribute name with underscore and then the class name. Calling dir on the class, again, we can see that we have the value 1 here when accessed from the instance. A descriptor is an object attribute with binding behavior. But what does this mean? Its attribute access has been overridden by methods in the descriptor protocol. These methods are dunderGet, dunderSet, and dunderDelete. If any of those methods are overridden, then that object is said to be a descriptor. The default behavior for attribute access is to get, set, or delete the attribute from its dictionary. Let's create a simple class with 2 attributes, x and y. We assign 1 to x and 2 to y. We instantiate it, and our instance is s here. If we want to access the attributes, we use the dot notation, and we type in s.x and s.y. Here, when we're accessing the attributes in this way, what's happening is Python is searching for the values of these in the instance dictionary. In fact, we can have a look at the instance dictionary if we were to type in s.dunderDict. So that's 2 underscores, dict, and then another 2 underscores. That's the instance dictionary. And if Python doesn't find the key there, our keys in this case being x and y, then what happens is that Python then goes and tries to find these keys and the values in type a.dunderDict and then the key in square brackets. Recall that type A, in this instance, it would give us the class. So first Python looks in the instance dictionary, and then if it's not there, it has a look in the class itself. This is called the lookup chain, and if the keys weren't found in the class, then Python would continue to look through the base classes of our class, which isn't applicable here, also excluding any meta classes. Now let's implement a descriptor and invoke it. Recall that I said the descriptor protocol was when dunderGet, dunderSet, or dunderDelete, if any one of the 3 had been defined and overridden. Just call it var, and then self.val will be equal to the initial value, and set the name of the variable, and then we'll we use it. Let's alter our example here with the simple class to class. So we write the constructor for descriptor class, we'll make the value 1, and we'll call it variable x. What happens when we run our code this time? So look, we have retrieving variable x, and then 1, and then 2. What's happened is that we haven't changed any end-user code. We still have print s.x and print s.y, but what we have done is by using a descriptor, we've rerouted the dunderGet to our own dunderGet, and that's why we see retrieving variable x, and why self.val is returned, i.e. whatever value we pass to it in the descriptor constructor, in this case 1. What have we demonstrated here? We've demonstrated that we don't need to change end-user code to make massive changes in how the program runs. Sure, here we're only printing what you'll
Let me type it here again. Test. Pancake. I wonder if we can just do the attribute. Chocolate. Cake. Print as attribute. Okay. Chocolate. Now it's false. Let me do this. So double underscore is double underscore is actually private from Python thing, from Python convention. This still returns true. But if I make it like this, it's probably going to turn false again. Yeah. So double underscore is actually private. Where's the delete thing? Watch this video instead now.
Okay, today we're going to talk about the class method built-in function in Python 3. I bet you might not know that class method is considered a built-in function. I didn't know that until recently. So let's take a look at class method. Class method is a decorator, which is how I generally consider it, and it transforms a method into a class method. Sounds about right. The first argument is the class itself, and then it can take arguments from there, and we use it by using this at syntax and just at class method above a given function. I went ahead and created a car class for us. It takes features as an argument. We have a little repper to print it out nicely, and then we have our class method. So it looks like a normal decorator on top of the function. Only one mandatory argument of CLS, and we're going to return some features. But actually, even before we look at the class method, let's just review how to create a new car the good old-fashioned way. So we'll add one feature here called high beams. We can print this guy out, print out our new car. Cool. What does that look like? All right, new car, high beams. As an aside, we don't need this repper thing. I just have that in there to make it cleaner. So if we got rid of that, we print it. It doesn't look very nice, but you could just do it like this and print out the dictionary inside our object. And that looks clean too. But because I'm going to change around the print statement a couple times, let's leave this repper in here. Cool. So let's start messing with our class method. Actually, let's keep our high beams. I like what we're doing there. I like high beams. And let's say we want to create a new car with this class method. Let's invoke truck as so. We have to use, we are invoking a function, so that's why we're using this syntax here. And let's check that out. Clean that up. Print. Boom. New car, high beams. And let's say your boss comes along and says, actually, every new truck needs to have be 4x4 and needs to have big tires. So print that out. That's what that looks like. So let's say we have another car in our car portfolio in our garage, and this one, oh, what's the problem here? Oh, that's fine. Okay, so let's say we have a sports car, right? Then we can invoke the new sports car as such. Sweet. Oh, right, we have the same parameter. So let's give it some new ones. So let's say it only has 2-wheel drive. Let's say it has sport tires. Run that. Cool, here's our new car. Going back to the docs real quick, we know that there are optional arguments we can pass to it. So let's see what that looks like. Let's say, what kind of argument do we have? So let's say our sports car has different like sports packages. So we can create packages here and have a little if statement and say if package equals, let's say, what are some? So SRT, that would be good. So if we have an SRT package, then we can return this, maybe say it's got 300 horsepower. And then when we invoke it, just add that as our argument. Cool, so here's our new car, 300 horsepower, all that. And if we want to have more than one package, we can just create a new if statement, maybe call this one Hemi, pretty sweet. Give this a whopping 500 horsepower. Maybe this one could be 4x4, whatever, 2x4 is fine. And we'll say it has racing tires. And so when we create our new car, we just ask for a Hemi. Boom, 500 horsepower, racing tires, looking pretty good.
So it acts like a class, pretty much.
Hey Thinksters, and welcome to today's video. So sometimes, very seldomly I get asked, what is the dog string in Python? So for example, you have an object, say an object dog, and your dog does something or nothing, it doesn't really matter, so you have a method. So like functions within objects are called methods, they are associated to the object itself. And now you could, for example, you can create a dog, say bello. You create a dog like this, okay? And then you can for example call bello do nothing or so. So now this is, say, the overall structure of our example. And now where does the dog string come into play? So the dog string is if you use triple quotes to define, so now you can use triple quotes for each method and for each class, for each object, for each function, anywhere. So immediately after the definition, you can have a dog string. For example, you can have your best friend here for the dog example. So this immediately follows after the definition. For example, you can have a dog string for the object. You can have a dog string for the function. does nothing really. So it explains what the function does, what the doc does. It gives you some contextual information, or the user of your functions and your definition. So this is considered good style to have a doc string. Okay, the doc string explains what the thing does, what the thing is. And now interestingly, you can, for example, anywhere you define. So for example, in the code you can do, you can call bello, for example, dog. Okay, and you can access the doc string with this underscore dog underscore notation. So this double underscore is also called for short dunder in Python. So we have a dunder method dog, and we can access it by just calling bello.dunder dog. And we can also like print the same thing on the doc level, on the doc class. So this is how we can access the doc string, and now we can print it. Do nothing takes one. Okay, I have to use a self here because it's a class definition. Okay, and you see now the output is your best friend. So the output is the doc string. We didn't do something like this equals to something. So this we didn't do. I mean, then you could expect that if you access doc or bello.dunder doc for the doc string, then this would be the output. We didn't do this actually. Python does it like internally. They automatically assign the first string enclosed in triple quote that follows the definition. They assign it to this variable underscore doc underscore. This is a doc string. And now the question is, where is it used? Why do you need it actually? And so there are many applications. For example, if you create your own code, your own code base, like a module, for example, a Python module, that you make public to the world, okay? So everybody can access this module. Then you can use the Sphinx Python documentation generator, and it creates such a beautiful documentation. So let's maybe quickly get rid of my face here somehow. So now you can access this you can generate this beautiful documentation completely automatically, okay? So it's like you don't have to do anything to do this. You just have to use the Sphinx documentation generator to create this HTML documents, to create this web documentation, okay? So you can have, for example, getting started, you will have the functions here. You can access the functions like this, and users click on your function, and they see the explanation of your function based on the doc string, okay? So doc string gives you the power of generating meaningful documentations automatically by means of a tool like Sphinx or so, okay? So, and this is not only the only thing, but also if people will use your objects there and they, for example, they don't know what to do about it. So if they, this wouldn't work here, I guess. If I have bello dot something, do nothing, okay? Say do nothing. Then it will give me some tooltips. So this is, this only advanced code editors like IDEs have these functions. But for example, if I type this do nothing, then I don't know this function, what does it do? So while I type, so advanced IDEs have this functionality, I type do nothing, then it proposes the correct method, do nothing, and it also gives me information about this method. What is it about? And this is done dynamically. So as I type this in, I see, okay, the do nothing method does nothing really. Okay, so I maybe I use another method. Or as I create a doc, so as I create this doc object, it then automatically tells me, doc is your best friend. Okay, so it will automatically give me these tooltips and this information. And this is for, it's considered very good style to have this doc strings. And so there's an advanced kind of best docstring convention. So there are some conventions about the docstring. For example, so because docstrings should be they should be very standardized so that people understand them. You should not put things maybe like this into your docstring. So docstrings should be meaningful, and there's like a whole standard you can check out the docstring standards. So in many cases, you should try to have one-line docstrings if it is possible for obvious cases. Yeah, and you should use triple quotes. Yeah, you should use no blank line either before or after the doc string, so it should come immediately. Here you see it comes immediately after the class definition. Of course, you could do something like this, have a blank line, but you shouldn't actually add this blank line. The doc string is a phrase ending in a period, so it prescribes the function or method's effect as a command. Do this, return that, not as a description. So for example, not returns the path name or something. It should be like do function. This should returns nothing. Period. Okay, so this would be considered a good doc string. And so it should give you the information what it does, and it should not describe it. Okay, so it should give you directly the return thing or what it does as an action phrase. It should not be a signature that just iterate the same thing. So you should not do something like this. Do nothing self. So it should not like give exactly the same signature that is already in the function definition, because this doesn't provide any meaning. It is better to write something like do x and returns nothing. Yeah, for example, this would be a good doc string because it has some meaning. It should be this was for this. Then we does what it returns and gives you some more information about the keyword arguments. Okay, so you can have some very be accessed by applications and best practices for defining doc strings, but this shouldn't mean that you should not try it out even if you haven't read the specification. So just try the doc string and then optimize over time. Then you can look things up. For example, should this start with a new line or not? So it is considered best practice to have the opening triple string and then immediately start with documentation, not starting with an empty line, but then in the end to have an empty line like this here. We could of course do the same like this, but this is considered like worse than this one. Why? Yeah, because you can immediately see the opening and closing triple quotes. They are at the
So it brings the path to the module.
This video will show you a possible solution to the error popping up on your screen. So let's begin.
Just an ad. Fuck you. What does the file variable mean do? When a module is loaded from a file in Python, file is set to its path. You can then use that with other functions to find the directory that the file is located in. This is really interesting. From a file in Python, file is set to its path. So maybe I can use that instead of naming the module. I can just put the sklearn.file, and that's gonna read the path. And then use that with other functions to find the directory that the file is located in. Okay, good. Next one. Probably gonna have to review these things eventually also. This class was
To use a new
this is about generators. The documentation is defined is that classes will have a module attribute. It seems the way CPython does that. This is that it defines a local variable module at the beginning of the class block. This variable then becomes a class attribute like any other variable defined there. You can find in documentation saying that the module has to be defined in this way. In particular, I can find any documentation explicitly saying the attribute has to be defined as a local variable in the class body. So being assumed and assigned as a class attribute. I'm guessing this is a CPython implementation detail that was carried over to other implementations. So I guess it's just like it says here. Oops. Gives the name of a module in which this class was defined. So you call a class, then you call this, and it's gonna give the library, the file in which the class is in. This might be useful in the thing because when I'm finding the imports, I can use this to find the class of the files of these imports. No, but I need the name of the class, so it doesn't work. Name of module in which this class was defined. What I need is the other way around. I need the name of the classes when I have the name of the file. When I have the name of the module. module which like other programming languages, Python is not designed to start execution of the code from a main function explicitly. Special variable called name provides the functionality of the main function. As it is an inbuilt variable in Python language, we can write a program just to see the value of this variable below. Running the above code gives us the following result, main. As you can see, the above value of the name variable is of string data type and equals to main. Below are two key features of name variable. When you run any well-written standalone Python script, which is not referring to any other script, the value of name variable is equal to main. Let's write a program named standalone py to illustrate this feature. Expected, so which main variable will be used? When you run a function from the imported script, name variable will evaluate the actual name of the script and not equal to main. But when you find out the value of the name variable from the recurrent program, both referring to the imported script, it will evaluate to main, as expected, as that is the scope of the program at level 0 indentation. Below program illustrates the example. Output running the above code follows the results. What of name is standalone. The usefulness of this approach is when the code if name equals main is used, the Python interpreter checks if it's parsing the currently executed script or if it's temporarily parsing another external script. This way the programmer has the ability to control the behaviors of different parts of the program by choosing to run lines of code from the external script as well as the currently executed script depending on the scenarios. So it's kind of like I saw on the video already from Corey. But if you're importing a file into another one, then the name of the file is gonna be equal to the name of the file and not main. And the current script is always main, and the other ones are the name of the file. So you can use if name equals if name is equals standalone, then you run some function, and if name equals main, you run other functions. Right, next. Probably gonna forget a lot of this stuff. I'll have to review it later. Designer code object containing compiled function bytecode. This one should be interesting. I keep closing this tab after. Should just leave it open. Yeah, people don't talk about this special names. Maybe this video talks about it. So I'm gonna search for articles instead. We can just look in the documentation as well. I don't even remember when I opened this tab here. Maybe this is interesting to read. I'll also have to review circular imports to understand better, because this script was giving a problem on the circular imports. So, yeah. How Csv modules loads circular imports. Depending on how main initialize main spec as set properly or to none. When Python is started with the /m option, spec is set to the module spec of the corresponding module or package. Spec is also populated when the main module is loaded as part of executing a directory, zip file, or other sys.path entry. The remaining cases, main spec is set to none. So how sys modules loads circular imports. There isn't a video, I'm gonna just search articles. Time for the articles. This is about the code thing. Code objects are simply looks into different aspects of a compiled function. Code object describes different aspects of a function based on its byte code. The exposed variables details about a function such as the number of positional arguments it must have, the number of its local variables, its free variables, and so on and so forth. All these details regarding a function are collected when the bytecode for the Python program is generated. That's why these objects are called code objects. They basically represent information given the bytecode. Every function in Python has a code attribute that holds its code object. This attribute contains a reference to the code object for the function. In the sections below, you'll see how code attribute. Specing the code attribute. The code attribute is one of the many attributes available in Python. The Python functions. As stated above, it represents the code object for the function. Simply defines a function f and returns the provider value. Let's inspect the code. We get back some representation of the code object, which is almost useless to us. Inspect further attributes. Based on the docs Python, a code object has the following properties. Co and locals is the number of local variables used by the function. Co arg count is the total number of positional arguments. Co var name is the tuple containing the name of local variables. Co name is the tuple containing the name used by the bytecode. Co cell vars is a tuple containing the name of local variables. Co free vars is a tuple containing the names of free variables. Now I'm not gonna read these other ones. What is the total number of local variables? So it's pretty much the structure of the object. Okay. Tuple of any default values for arguments. The documentation func defaults is documented as writable, so it would seem to be defined behavior. Like, oh, here. The inspect module provides several useful functions to help get information about live objects such as modules, classes, methods, functions, tracebacks, frame objects, and code objects. For example, it can help you examine the contents of a class, retrieve the source codes of a method, extract and format the argument list for a function. Get all the information you need to display a detailed traceback. There are four main kind of services provided by this module: type checking, getting source code, inspecting classes and functions, and examining the interpreter stack. Types and members. The get members function retrieves the members of an object such as a class or module. The function whose names begin with is already provided as convenient choices for the second argument to get members. Documentation string. So here there's a list of all of them. File name, documentation string, the name, qualified name of module, class was defined, documentation string. So attribute method, function, function object containing implementation of methods, instance to which this method is bound or none. Name of module in which this method was defined. Documentation string. Trying to think about cases where I might need to use this, or it might be interesting to use this. I think one thing that it might be good to do is go over some code that I have and use these functions, kind of like practice to see what happens. So, but I think I will do that another time. Tuple for any default values for positional keyword parameters. So when you create a function and you have default values for the parameters, it's going to return this tuple here. Global namespace in which this function was defined. So this goes back to the namespace thing. When Python is importing modules, it's gonna search for the module, then load the module, then attach to a namespace, which is the scope of the execution. And this attribute apparently shows that. It shows the namespace in which the function exists. Global namespace in which function is defined. Built-in names, annotation, mapping of parameter names, annotation, return. Keys reserved for return annotations. Traceback, name of module in which this function was defined, frame object at this level, index, current line, dbnx, next inner traceback object called by this level. This is interesting. Name of module in which the function, the frame object at this level, index of last attempted, instruction in bytecode, current line number in Python source code. Next inner traceback object called by this level. Next outer frame object, this frame's color. Next outer frame object, this frame's color. Next inner traceback object called by this level. So this might be useful to create the stuff that I want. Built-in's namespace seen by this frame. Built-in's namespace. This is interesting. Maybe I can do the same thing that I was doing for the graph things with Vivax. I can put this F built-ins here and figure out the scope of execution of the libraries, the namespace that they exist. Code object being executed in this frame, global namespace seen by this frame, index of last attempted instruction in bytecode. Yeah, so far this is the most interesting section, I think, for me. Line number in Python source code, local namespace seen by this frame, tracing function for this frame or none. Local namespace seen by this frame. I'm definitely gonna put this on favorites. Tracing function for this frame or none. Number of arguments not including keyword only arguments. String of raw compiled bytecode. Tuple of names of cell variables. Tuple of constants. Name which name of parts score bitmap. Number of positional only arguments. Number of keyword arguments. Name with which this code object was defined. Tuple of names of local variables. It doesn't show how to use it though. I assume it's with dot notation. Here's on the code block. That's the problem here. Which machine stack space required? Generator, var names, type of names, arguments, and local variables, name, qualified name, frame is the general running code. Object being iterated by yield from or none. Name, qualified name, object being awaited on or none. The coroutine running code where coroutine was created or none. This is .set coroutine origin tracking path. Implementation, self, instance to which a method is bound or none. The name attribute of generator is now set from the function name instead of the code name, and it can now be modified. Attributes to coroutines, built-in attributes to functions. Inspect.get members. Return all the members of an object in a list of name value pairs sorted by name. This is the inspect module that I was using before. And it's built in from Python, I believe. Return all the members of an object in a list of name value pairs sorted by name. If the optional predicate argument, which will be called with the value supplied, only members for which get module name, return the name of the module named by the file path, without including the names of enclosing packages. The file extension is checked against all of entries in part. The file extension is checked against all of entries in the import lib machinery all suffixes. If it matches, the final path component is returned with the extension removed. Otherwise, none is returned. Note that this function only returns a meaningful name for actual Python modules. Thus, the potentially referred to Python packages will still return none. Return true if the object is a module, it's a class, it's method, it's function. Return true if the object can be used in await expression. Oh, maybe this is interesting. Because I can use the inspect.isAwaitable. Let me try this actually. So instead of using a try except block, I'm gonna use this one. So here on line 73, well, where is the, oh, here. I was doing like this because of the mistake there. So now if I try to run this with sklearn 0, it gives me a mistake. But now I'm gonna have to import spec here. Now where's the line? If maybe I should just do if module. If is available. If it isn't available, oh. Pass. Else. Let's see if this runs. It doesn't run. It's weird because I would think that a circular import is available because the problem that it was giving was in the async IO function or module or whatever that thing is. Cannot import name context from partially initialized module. Let me see what this prints. I can't print this. Oh, no. I'm sure that I can't use break here. So how do I stop the thing? I didn't print anything. Yeah, whatever. Doesn't work apparently. Return true if the object can be used in a weight expression. It can also be used to distinguish linear-based continuous. Is a sync at gen function. Return true if the object is an asynchronous generator function. Change the version 3.8. If the object is an asynchronous generator function, generator created by. Is traceback. Return true if the object is a traceback. Return true if the object is a frame. It's code if it's built-in, routine, abstract. Retrieving source code. Inspect.getDoc. Get the documentation string for an object. Get comments. Turn in a string any line of comments immediately preceding the object source code. Returns the file, module source file. Yeah, so I guess I don't need to read this anymore. This is also cached. I still need it. Cache is an encrypted file of similar files. What do they do with the PyCache folder? When you run a program in Python, the interpreter compiles it to bytecode first. This is an oversimplification, and stores it in the PyCache folder. If you look in there, you'll find a bunch of files sharing the name of the Py files in your projects folder. Only their extensions will be either .pyc or .pyo. These are bytecode compiled and optimized bytecode compiled versions of your program's file, respectively. As a programmer, you can largely just ignore it. All it does is make your program start a little faster. When your script change, they will be recompiled. And if you delete the files or the whole folder and you run your program again, they will reappear as specifically suppress that behavior. When you're sending your code to other people, the common practice is to delete the folder, but it doesn't really matter whether you do or don't. When you're using version control git, this folder is typically listed in the ignore. If you're using C Python, which is the most common as its reference implementation, you don't want that folder. Because press. It's weird that this method is not here along with the other ones. I'm not sure if this was on this file on the other one. Oh, this is different stuff. This is the implementation of the import lib library. Oh, cached here. String for where the compile module should be stored or not. Compiled module should be stored. So it tells where the compiled should be stored, where the module should be stored. Yeah, it doesn't exist on this thing. But I think this is pretty much done for me. Now I just need to. I'm gonna erase this. Decorator functions, relative importance. Buffer, I still need to know what it is. Typing overload is probably some special decorator as well. So now I'm gonna watch the video about generators.
syntax to create more elegant iterators, essentially. All right, so let me start by introducing a problem to you here. Let's say we didn't have the function range and we didn't have a while loop, okay? No while loop and no range function. And we wanted to loop through the numbers 1 to 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, without using the range function, and without using a while loop, and without coming up with something super creative, just simply thinking about this, what we would probably do is the following. We might create some list, right? And then in this list, we could store our numbers 7, 8, 9, and 10, okay? And then what I could do is I could just loop through this list, right? I could say for element in X, and then I could just print the element. And quite simply, this is going to loop through all of these values. We're looping through the numbers 1 to 10. Now, the problem with this is that I'm storing these 10 numbers here in memory, in a list. And for me to be able to loop through them, I need to store all of them in a data structure. Now, that's not very efficient, and with 10 numbers, this is fine, but you can imagine if I wanted to loop through 100,000 numbers, a million numbers, a billion numbers, it really doesn't make any sense at all for me to store the entire sequence of numbers in memory, especially if all I'm going to do is process them one at a time, and I don't need to know what all of these are as I loop through numbers. So it doesn't make any sense for me to store this in a list. And that is why, of course, we use something like the range function, right? So I say for, I guess I won't say element, in this case I can say I, for I in range, and then I do something like 1 to 11, and then I print element. Here, I get the same thing. Oops, sorry, I'm going to print I, not element. Here, I get the exact same result.
Let's see where he's going with this.
Right, looping through the range of 1 to 11, except when I use the range function here, I don't actually need to store all of the numbers 1 through 10 in a data structure. And so if I were to look at the size of this data structure versus the size of the range function, we should see that this data structure has a larger size than the range function because the range function doesn't need to store all of these numbers. And in fact, if I want to do that, I can. So I'm going to import sys, and I'm going to say print sys.getSize of x. We can see that that is giving us a value of 136, and then I'm going to take my range function here. I'm going to print sys.getSize of, and then of the range function. Does that look good? Okay. And we see that we get a size of 48 for the range function. So obviously this doesn't prove exactly what I'm saying. I'm just trying to show you that this uses more space than the range function because the range function doesn't need to create this list for us to be able to loop through it, and that is because the range function returns to us an iterator. Okay, so now we can really talk about what an iterator is. So an iterator, as I described before, is really something that allows us to loop through a sequence of numbers or of some data without having to store them all. So the range function is a great example of an iterator because it lets us loop through all these numbers without having to store them in some data structure. I'm going to show you one more example of an iterator in Python that you may not know is an iterator, and just kind of describe briefly how that works because it will bring our understanding. So I'm going to use this function called map. If you don't know what it does, don't worry. Once I write the code here, I'll explain exactly what it does. I'm going to say I to the exponent 2 and then pass x. Okay, so what the map function does is it takes some data structure, in this case we have a list, and it maps all of the values in this data structure to some function. So pretty much it applies this function to all of the values in the data structure, and then actually returns to us an iterator that contains all of the results of this function called on all of these values. So essentially what this is doing is generating the squares of all these values. And so if I were to look at this as a list, I would have 1, 4, 9, 16, so on and so forth, because I'm applying this function right here, which is just generating the square of all the values from the list. Now the thing is, this map function here doesn't actually store a new list that has all of the results of these function calls. This function here is actually a generator or an iterator that allows us to iterate through all of these results, so all of the results of these values passed through this function without actually storing. I understand that's a little bit confusing, but if you look at y, if we print out y here, we see this is a map object. This actually isn't something that's storing all of the values. It's not a list, right? Now, if I were to look at the list representation, so I print out the list, we see that we do get all the values that we expect, but this is not the default behavior. It's not storing this list. It only creates this list for us when we call this list function. That's a common misconception. So let me show you what I mean and how this is actually an iterator. So if I go something like for I in y, and then I print I here, we see that we get all of the values that we expect. The thing is, we only generated these values once we started looping through this map object. They weren't already generated and stored in memory. Like when I say for I in y, on the first iteration, it sends this 1 to this function and gives me the result. Then it sends this 2 to the function, gives me the result, sends the 3 to the function, gives me the result. It's doing it while I'm looping through it. It didn't do it before and store all of it in memory. And to give you one last proof here, I'm going to print the sys.size of, or I guess this is get size of, and then of y. And let's see what we get. We get a size of 48. Again, if you compare that to, let's say, the list of y, okay, you'll see that the list of y is much larger than simply y, because when we do the list, it actually generates a list for us. Hopefully this is making sense. The whole point is that we didn't have to store the sequence in memory. We could generate the sequence as we loop through it, and that's really what an iterator is. Okay, so now I want to dive into how an iterator actually works and how you create an iterator. So really, what a for loop is doing is it's calling a special method on all of these iterator objects, so this map object, this range object, that gives us the next item or the next piece of data in the sequence that we're looping through. So there's actually this function here, and it's called next. And what this does is give us the next value in the iteration through an iterator. So if I go here, and I print the next of y, you can see that we get 1, right? And then if I print this again, we get 4. And if I print this, again, we get 9. And again, I did not mean to create a new file there, we get 16. And then notice here, right, I've gone through 4 times y. And now if I start looping through y, for I in y, and I print I, we're going to start looping at 25, because that was the next value in the iteration. Notice I didn't have 1, 4, 9, 16, and then those repeating again, and then looping through the rest of the values. It continued right at 25. And just to make this even more clear, I'm going to say print for loop starts, okay? And notice we have 1, 4, 9, 16, the for loop starts, and then we continue through the rest of the iteration. Hopefully this is kind of making sense, but really what a for loop is doing is it is calling this next function on your iterator object, and that is returning to you I, which is going to be the next value in the sequence. So when I've already looped through the first four values in the sequence, and then I go to the for loop here, well, the for loop is just going to continue to call next until eventually there's no more items in the sequence, and so that's why it starts after we've already looped through the value, if that kind of makes sense, or it starts where we left off looping through the rest of the sequence. Hopefully I'm articulating that. Okay. So hopefully that makes sense, but that is what an iterator does. That's what a for loop does. An iterator has this kind of next method on it, and when we use this next function, well, we get access to the next value in the sequence. Now, the same thing works when I do this. Y dot underscore underscore next underscore underscore. So this is a dunder method, a double underscore method. Some of you may be familiar with that, but the next function is the exact same as me calling underscore underscore next underscore underscore on an object, and to just show this to you, if I run this, you see we get the same thing. Okay, nice. So that is how that works. Now, what I'm going to do for you is write a for loop, or write what the actual implementation of a for loop is, so you can see how it actually works on an iterator. So this is our for loop, but if I were to write this for loop and kind of peel away, the disguise here where it says for, this is what it would look like. If I say while true, and then I'm going to try to get the next value in my iterator. So I'm going to say value equals next, and this is going to be of y, and I'm going to accept. The exception here is stop iteration. I'll describe this in a second, and then I am going to break, and I'll just print done, and then here I will print the value. Okay, so these here, this for loop and this while loop are actually identical. Let me get rid of this though, because we don't need this anymore. Okay, again, yeah, so this for loop and this while loop are identical. We are looping through this y iterator. So in this case, I'm saying for I in y, and then what this for loop actually does is what I've written here. We have an infinite loop, so we have while true because we don't know how many items are in the sequence, and then what we do is we try to get the next value from our iterator. So we keep calling this next function, or in the same way we could say y dot underscore underscore next underscore underscore, but the next function is kind of convention. Then we print out the value, and then we accept stop iteration. So if at any point in time there is no more values in the sequence or in the iterator is going to raise an exception. This exception is stop iteration, and in that case we end the while loop and we're done. So just keep in mind, this for loop and this while loop are literally the exact same thing. All right, so let me delete this for loop here and just run this for you, and you can see that this works. Right, we print out all the values, and as soon as we find the stop iteration error, we print done. Now let me show you what happens if I don't have this this exception. So if I just do this, I just try to get the next value from my iterator, and I run this. Notice we get an exception, and it just says stop iteration. That's obviously why I accepted the stop iteration error, because well, you need to do that, otherwise your program is going to crash, and that is exactly what a for loop does. Okay, so there you go. That is the basics of how you loop through an iterator. Now let me show you kind of doing the same thing, sorry, with the range function. So let's say x is equal to, in lowercase, x is equal to range, and then we have 1, 11. That's the range we want to loop through. So let's start by just printing x. Now notice when we print x, we actually just get a string representation of the range function. So this is a string, it just prints this out for us. And now watch what happens if I try to call next on x. If I do this, notice we get an error. It says range object is not an iterator. Now the reason it's not an iterator is because for us to actually get the iterator from the range object, we need to call another special method, which is called iter. So there is this iter method, or this iter function, sorry, that returns an iterator from an object, and there's also the dot underscore underscore iter underscore dunder method. Now what this iter method does is the exact same thing as this iter function. If you call the iter method, it's literally identical to calling the iter function, just like the next function and the next dunder method. So the whole point of me saying this to you though is that if we want to get the iterator from x, we need to call iter like that. So if I call iter there, now this is actually going to work. Right? I get the next of iter x. We don't get an error. I didn't print out what that was. I can print it. You can see that that is now correct. There you go. So that is kind of how that works. So the whole thing is when I do something like for I in x, what actually happens is we're saying for I in the iter of x, and then it calls the iter method, gets the iterator, and then calls the next method on the iterator object that we got from the object we're looping through. Hopefully that kind of makes sense, but the whole point is you start by calling that iter method. That iter method returns to you the iterator, which has a next method on it, and then you call the next method on the iterator. It's a little bit confusing because on map, you don't need to do that. On range, you do need to do that. The whole point is that there's kind of two methods that make up an iterator. One is the iter method, the next is the next method. So now what I'm going to end off the explanation of iterators by doing is showing you how you make your own iterator using kind of the old legacy syntax, not the generator syntax. So the way you do this is you create a class. So I'm going to make a class. I'm just going to call this class iter. Now you can define the init and any other methods in this class just like you would for any other class. So I'm going to say self. I'm just going to take some value n. I'm going to say self.n is equal to n, and n will kind of be like the maximum value I want to go to while I'm iterating. All right. Then if I want to make this an iterator, I need to implement two methods. Those methods are iter and next. So I'm going to say define underscore underscore iter like that. And all I'm going to do here is I'm going to return myself. And I'm going to set self.current equal to 0. So when I call the iter method, I'm going to initialize something, this current variable is going to store the current value out of my iteration, and then I'm going to return myself. The reason I'm returning myself is because I'm not creating any special iterator object here. I'm just returning this object itself, the current instance that I'm calling this on, so that it can use that as the iterator. Might be a little bit confusing, but we'll keep going. So now I'm going to implement the next method, so underscore underscore next underscore underscore. And inside of here, what I'm going to do is say self.current plus equals 1, and then I'm going to return self.current. Now I need to change a few things. First, I'm going to make self.current actually equal to -1. And before I return self.current, I'm going to say if self.current is greater than or equal to self.n, then what I want to do is raise stop iteration. Okay, this is kind of the way that you need to implement iterator. Inside of your next method, you have something, some base case that raises the stop iteration, or some exit case that raises the stop iteration, and then you increment your iterator or do whatever it is you're doing with your sequence, and then eventually you return the value. So the reason I'm initializing current at -1 is because I start by adding 1 to whatever my current iterator value is. So -1 goes to 0, so the first value I return is 0, then 1, then 2, so on and so forth. And then eventually I raise the stop iteration error, and it's not until I call this iter method again to get a new iterator do I reset my current value to -1. Okay, hopefully that kind of makes sense, but let's just make the iterator now. Let's say x is equal to iter. Let's pass the value 5 in here, and now let's try to loop through this iterator. So I'm going to go 4, and I'll say I in x. I'm going to print I, and let's see if we get an error. No, we don't. We get 0, 1, 2, 3, 4. There you go. So we just create an iterator. We can now loop through this object because we have the iter method and because we have the next method. Now watch what happens if I remove the iter method. If I remove this, it says iter object is not iterable. The reason it's not iterable is because it couldn't get the iterator from it because we didn't implement the iter method. Now let's remove this next method and let's see what happens here. Returns non-iterator of a type iter. So it returns something that didn't have the next method on it. So that means it is not an iterator. Hopefully that is clear, but that's how that works. Okay, so now let me just show you how we would manually call the next method on this. So I could do something like print and then next of x. But when I do this, take a guess at what's going to happen. Notice I get an error. It says iter object has no attribute current. The reason it has no attribute current is that I didn't create the iterator object first, or I didn't initialize the iterator by calling the iter method. I just called next. So I would need to say like itr is equal to iter of x, and then I could call next on itr. Okay, and then notice I get 0, and then if I call it again, so let's do it here, I get 1, 2, 3, and so on and so forth. Okay, so that is the old school way of creating an iterator. Now I'm going to introduce to you generators, which is the much more elegant and nice way of creating an iterator. So the generator syntax is quite simple. You create a function. So in this case, I'm just going to say define gen. Take in any parameters that you want. In this case, I'll take in n. And then what you do is you use the yield keyword instead of the return keyword. I'm going to explain exactly how this works, but let me just make the exact same iterator I made before using the generator syntax. So let me say, actually I don't need self. I can just say, we use a for loop actually, for I in range, and then this will be n, and I'm going to yield n. And I need to spell yield correctly. I'm going to yield n. Okay, so this is exactly the same as that class that I just created, and notice how much simpler this is. So I'm sure this probably still doesn't make much sense to you, but let's just loop through it. For I in, and then we're going to say gen of 5, like that, print I, and notice that we get, oops, sorry, it's yielding n, that needs to yield I. My bad, we get the exact same thing that we got before. So the way that the generator works is when the yield keyword is hit, it pauses the execution of the function and returns this value to whatever is iterating through this generator object. So in this case, I'm saying for I in gen 5. So I'm looping through my generator here, passing the value 5 to it. And inside of my generator, I create this for loop. And in this for loop, I'm looping up to 5 or up to n. So in this case, 5, but not including 5. And I'm yielding I. So as soon as I get through the first iteration of this for loop and I is equal to 0, I yield 0. And what that means is I immediately pause, I stop. All of the information about this function is saved, so it's stored in memory. And then I go to this for loop and I print whatever the value is that I yielded. Then what happens is the function, or this for loop continues. So we go to the next value we call next on this generator. That then has the for loop run again. So then we get the value 1. Then we call next again. We get the value 2, 3, 4, so on and so forth. The important thing to understand is when yield is hit, the function execution is paused. It's not terminated, it's not done, it's paused. And then we return to it and continue running whenever we see the next keyword again, whenever we call the next method or function on this generator. So to do this manually, I could say, I guess I'll just go x is equal to gen of 5. And I could say next x. Let's just print this like this. Okay, so if we do this manually, okay, notice we get 0, 1, 2, 3. So pretty much this generator syntax makes the next method and the iter method implemented for us, so we don't have to manually write them inside of a class, and instead we just use the yield keyword. Now I'm just going to show you in a different way how we could do this. So let's say we take no parameters here. What I can actually do inside of this function is I can yield multiple times. So I'm going to yield 1, then I'm going to yield 2, then I'm going to yield, again, I got to spell that correctly, 3, then I'm going to yield 4. So now when I do this, notice we get 1, 2, 3, 4, because what happens is we yield 1, we pause the execution of the function, we print the value. We yield 2, we pause the execution of the function, we print 2, right? So on and so forth. And if you want to make this even more clear, we're going to print pause 1, okay, pause 2, pause 3. And actually, now that I think of it, yeah, okay, this is fine. Yeah, we can do that. So let's run this and notice we get 1, pause 1, 2, pause 2, 3, pause 3, and then finally we have 4. And the whole point is that we didn't need to generate this entire sequence of numbers to be able to loop through it. We were just returning it as we needed those values. All right, so at this point in time, you're probably asking yourself, what's the point of this? Maybe you understood the examples I went through. You know when you use the yield keyword in a function that generates a generator or makes that function a generator. And as soon as you hit the yield keyword, the execution of the function is paused, but the entire state of the function, all variables, everything inside of it is saved, right? All of that's saved, but the execution is just paused and then it can be returned to when you call the next function. However, again, what is the use case of this? Well, really, the use case of a generator is such that you can loop through a sequence or some large amount of data without needing to store all of it. And the situation in which you use a generator is when you do not care about the data before or after something in an iteration, you only care about the current piece of data that you're looking at. So a super simple example is you want to print out all of the numbers in a sequence. You don't need to know the previous or the next number in the sequence or any, of the numbers in the sequence. You only need to know the current number in order to print it out. And there's a lot of times when you're looping through some type of data structure or something where you don't care about anything before or after the current element, you just care about the current element. And if that's the case, you use a generator. However, if you do care about stuff forward or after, or I guess, sorry, before or after the current element, then you can't use a generator because you need access to whatever's before, whatever's after. Maybe you need access to everything that's to the right in the list, everything that's in the left of the list, or sequence or whatever. In that case, you can't use a generator because the generator only gives you the current value. You could have a generator give you maybe the second, third, fourth value, but if you need access to the entire sequence when you're processing one element, you can't use a generator. Hopefully that's clear. That's kind of differentiating factor on when you use a generator or when you would use some data structure to loop through. But I want to give you a very real example here of when you use a generator. So let's say you have a very large file, maybe a file that has billions of lines in it, or just a ton of lines. It's going to take maybe like a few days of processing power to actually go through and process this file, depending on what you're doing with it. And let's say simply in this file, you want to look for if a word exists. You don't really care where it exists. You just want to know if a word exists in this file. Well, the first way you could do this, find if a word exists in the file, is you could read the entire file. This would be the standard way. You read it all into memory, and then you loop through the data structure you have that represents the file, and you see if that word exists. That's the first way that you could do it. However, you don't need to know every single line in the file at one point in time. You only need to know the current line that you're looking at, and then you can determine with the current line if that line has the word that you're looking for in it. So you look at one line at a time. You don't care about all the lines before, all the lines after. You only care about the current line. If you find the word great, if you don't, you move on to the next line. In this situation, you would use a generator. And what you could do is yield one row of the file at a time, so that rather than reading in the entire file and taking up maybe gigabytes of memory, you're only taking up a few megabytes or gigabytes or bytes in your memory to store one line at a time. And then as you look through that line, you move on to the next line if it doesn't have the word, or maybe you stop the program if it does have the word. So I'm just going to copy a function here that shows you exactly how you do that. This function is called Csv Reader. And all you do is you pass a file to this function. What it does is it opens the file and then it yields one row of the file at a time. So this way, you don't actually need to read the entire file at once. You just read one row. You can process the row, see if it has a word, and then continue on from there. So that is kind of my example. Hopefully that maybe cleared it up on when you would use a generator. So sorry for the abrupt cut here, but I realized when I was editing this video, I forgot to mention an important part of generators, which is generator comprehensions. So there's actually another way to create a generator that does not involve creating a function. Previously, the way we made a generator was made a function, and we just put the yield keyword in. As soon as you put the yield keyword in a function, it's a generator. However, another way to do this is with a comprehension. So let me just show you. Comprehensions. So there's actually another. I realized when I was editing this video, I forgot. So this way, you don't actually need to.
Oh, this is interesting. So I can read one row at a time.
To read the entire file at once. You just read one row. You can process the row, see if it has a word, and then continue on from there. So that is kind of my example. Hopefully that maybe cleared it up on when you would use a generator. So sorry for the abrupt cut here, but I realized when I was editing this video, I forgot to mention an important part of generators, which is generator comprehensions. So there's actually another way to create a generator that does not involve creating a function. Previously, the way we made a generator was made a function, and we just put the yield keyword in. As soon as you put the yield keyword in a function, it's a generator. However, another way to do this is with a comprehension. So let me just show you. I'm saying something like x is equal to, I'm going to put the syntax for a tuple, so open brace and close brace, or open parenthesis, closing parenthesis. Then I'm going to say I for I in range 10. Now this is a very stupid generator. You never make this, but I just made a generator. And to prove this to you, I'm going to print x. So when I do this, notice I get a generator object. So whenever you do a comprehension like this inside of the parentheses, this gives you a generator. So now I could print out the next of x, and when I do that, I get 0. I could do this again. Okay, I get 1, 2, 3, and then I could loop through x. I could say for j in x, print j, and well, we get the same thing, right? That's all I want to show you. That's another way you can make a generator with a comprehension like this. Of course, you would do something that probably makes more sense than this. That is a bit more advanced. There's another way to go about doing that. All right, so with that said, I am going to end the video here. I hope you guys enjoyed. If you did, make sure to leave a like, subscribe to the channel, and I will see you in another YouTube video.
Hey guys, it's the same thing. But I'm gonna watch more videos about it. Probably this show here.
Hey, how's it going, everybody? In this Python video, we're going to be going over generators and why you'd want to use them and some of the advantages that they have over lists. So in this example, I have this function up here called square numbers, and what it does is it takes in a list of numbers, and then we have this result variable, which is set to an empty list, and then we loop through all the numbers from the list that we passed in, and we append the square of that number to the result list, and then after we're done looping through all the numbers, then we return the result. And then you can see here, I have this my numbers variable set equal to square numbers. I'm passing in a list of 1, 2, 3, 4, 5, and then I just print out my numbers down here. So if I run this code, then you can see that our list of 1, 2, 3, 4, 5 that was passed in, our result is 1, 4, 9, 16, 25. So currently our square numbers function is returning a list. Now, how would we convert this to be a generator? Well, to do this, we won't need this result variable anymore, so we can take that out. We don't need the return statement, and this result.append, we can take this out, and all we have to do is type in this yield keyword and just yield the square number here. So this yield keyword is what makes it a generator. Now, if I save this and run it, you can see now whenever I print my nums, I'm no longer getting the list. If you look at the comment here, this is what the result used to be. I'm no longer getting 1, 4, 9, 16, 25, the squares of 1 through 5. No longer getting that result. I'm getting this generator object here. Now, the reason for this is because generators don't hold the entire result in memory. It yields one result at a time. So really, this is waiting for us to ask for the next result. So it hasn't actually computed anything yet. Now, if I print it out next my nums, which asks for the next result, then you can see that it's 1 because we passed in our list of 1, 2, 3, 4, 5, and then we're looping through that list. And so 1 is the first value, so it's equal to I here, and we yielded out 1 times 1, and it gave us that result. So now, if we copy this line here and print out next my nums a few times here and run that, then you can see that each time that we run next, it goes and gets the next value that's yielded. So now we have 1 squared, 2 squared, which is 4, 3 squared, which is 9, 16, 25, and so on. Now 25 is the last value from our result. So what if I was to run next one more time? Well, if I do that, you can see that I got an error here, and the exception that it threw was stop iteration, and that means that the entire generator has been exhausted, and stop iteration just means that it's out of values. Now, instead of getting these values one at a time, we still can use a for loop on these generators, and this is personally how I use generators a lot of the time. So let me comment out this line, and then let me uncomment that one and save it. So now we're saying for num in my nums, which my nums is our generator, print out num. So I'll run that, and you can see that we get all of our values, and we don't get the stop iteration exception because the for loop knows when to stop before that happens. So one immediate advantage over a list is that I think that this is much more readable here. Rather than having the result set to an empty list and then appending to that result and then returning the result, this is kind of more readable. We're saying, okay, I'm passing in these numbers for each number in that list of numbers, yield the result. Now, for those of you more familiar with Python, you might have noticed that this entire process here of these lines of code would have been much easier to write as a list comprehension. So let me comment this out. And if you don't know what a list comprehension is, don't worry about it too much. I just want to show the generator example with this as well. Now, this is a list comprehension here, and it's going to do exactly what our square numbers function did. So what we're doing is we're creating a list, and we are taking x times x, so the square of x, for x in this list of 1, 2, 3, 4, 5. So if I save this here and run the code, you can see that I still get the same results, and I can also print out this list up here at the top. Now you can create a generator in the same way, and it's just as easy as taking out these brackets and instead putting in parentheses. So if I take out those brackets, put in parentheses, now if I run this, then you can see that when I printed my nums here, tried to print it all at once, I got that generator object, and then when I ran my for loop, it looped through all the values and gave me that result. Okay, so what if you wanted to actually print out all of the values from the generator? Well, like I said, they're not currently all held in memory, but you can convert it to a list, and it's just as easy as just putting list and then wrapping that. And then if I run that, you can see that it printed it out just as if it was a list. Now, when you convert this generator to a list, then you do lose the advantages that you gained in terms of performance. And I haven't talked about performance yet, but I have a better example to show those advantages. So a generator is better with performance because, like I said, it's not holding all the values in memory, which isn't a big deal at all whenever you have a small list like this of 1, 2, 3, 4, 5. But say that you had tens of thousands or even millions of items to loop through, then having that many items in memory will definitely be noticeable, but you don't get that with generators. So whenever you cast a generator to a list like this, if this generator had a lot of values that needed to convert to that list, then you lose that performance in terms of it would put all of those values into memory. So let me show you a better example here of this performance difference. So I have a file here where some of this stuff you don't have to worry about, like these lines here, I'm just printing out the memory, and then these names and majors, these are just going to be used to make some random values. So I have two different functions here. One of these is going to make a list, and one of these is going to be a generator, and they're both returning the same values. So within this list, I have my result here, and I'm looping through a number of people that I'm going to pass to this function. And for each person, I'm just going to make a person dictionary, give it an ID and a name that's randomly chosen from the list of names up at top, and a major that's randomly chosen from the list of majors, and then I'm going to return that result. And for the generator, it's the exact same thing. I'm going to loop through the number of people that I pass in, and then I'm going to yield this person dictionary that has the same values as the list function had. Now, really quick, just to make these the same, I'm going to make that an X range instead so that these are exactly the same. Okay, so right here, don't worry about these lines here, this time.clock and this T2 time.clock. All I'm going to do is time how long it takes to run this function, which returns a list. Now, I'm going to pass in 1 million values to this function, so it should return a list of 1 million results. And then down here at the bottom, I'm printing out the memory usage and the total time that it took. So if I run this, then you can see up here at the top of the code, so this before here, this is before I made anything. So my base memory usage was around 15 megabytes. And this memory after is after I created that list of 1 million records. So you can see here that it jumped up by nearly 300 megabytes, and it took 1.2 seconds. Now, if you're dealing with large amounts of data, that's not out of the ordinary to have 1 million records like that. So let's see what this looks like if I instead use the generator example. So I'm going to comment out the function that returned a list, and now I'm going to uncomment this function that returns a generator, and I'm going to pass in the same number of values. I'm going to pass in 1 million values here. So if I save that and run it, now you can see here after I ran this that the memory is almost exactly the same. And that's because the generator hasn't actually done anything yet. It's not holding those million values in memory. It's waiting for me to grab the next one or to loop through those, and it would give me those one at a time. Now this time that it took here, basically it didn't take any time because as soon as it gets to the first yield statement, it stops. So if I was instead to make this an integer, then it would be nearly 0 seconds. Now, whenever I said earlier that if you convert this to a list, then you lose that performance, then let me show you what I mean here. So I will convert this entire result to a list. And now if I run this, then you can see basically I got pretty much the same result that I got when I ran the function that returned the list. So if I take these back off and just do the generator, then you can see that we get our performance back. So that's how you use a generator. I think that it is a little bit more readable, and it also gives you big performance boosts, not only with execution time, but with memory as well. And you can still use all of the comprehensions and this generator expression here, so you don't lose anything in that
So I
area.
have
So those are a few reasons why
theory.py opened, and I'm going to start off with talking about generators, and then coroutines, and then finally asynchronous generators. That's part of the theory section. After that, we'll actually produce a small application. Okay, generators, what are they? Generators are basically something in Python that produces a sequence of values. That sequence could be a sequence of integers, floats, strings, booleans, a sequence of any type of value. So what I'd like to do is I would like to produce a sequence of odd values starting at some starting point and ending at some stopping point. That's what I'd like to do. So I'm going to create a function called odds. And this function will have two parameters, one called start and one called stop. And so let's say the start is 3 and the stop is 15. That means it will produce the stopping point is actually exclusive. It doesn't include it. So I'm going to include it in the session. And odds is my function that I created. Now next is the built-in function in Python. If I say next,
I think I read
we'll
about
continue
it.
getting a stop iteration. Now you can actually produce another generator. And when you say list of a generator, what actually happens internally is it calls next, and it exhausts the generator until it's empty. So I can print X like that. And yeah, so now there was a couple different ways of causing this generator to run. One is I can just do next on it. The other one is I can call like some constructor function like a list or a tuple, for example, and that'll cause the generator to run. Or I can just use a for in loop, and that also causes the generator to run. So once again, this thing produces a generator, and the generator will run up until the yield point. It stops executing, and then once you call next again, it's like cranking the wheel. It cranks until the next iteration, cranks again, the next iteration. If I exit out of my
It's pretty easy to understand. Let me see if I can get to the struct.
Hey folks, how's it going? So this is a new video in the Python Tricks series. Python Tricks is a new book that I'm working on. It's like a buffet of awesome features in Python that show you, the whole book is organized in a way where there's small chapters that each show you a really cool feature in Python, like a really practical feature you can apply in your own day-to-day work.
Damn, it's crazy to me that this stuff is advanced. Or intermediate. Using get return default value from dictionary. I know a lot of these things here, but I don't consider myself intermediate yet. Finding automated patterns. I tend to make comparisons with going to the gym because that's what I know. And usually people that start going to the gym in the first year, this first 6 months they have the beginner gains, which is a massive growth. And then in the first year they're still in the beginning phase. And it takes usually around 3 or 4 years until you actually start getting to the intermediate phase, from my experience. And then around 5 or 6 years, then you can be considered somewhat good. And 8 years plus, then you're obviously advanced. But I'm not sure if for other things it works the same way. It feels like it should, but the way that people are saying these things, it seems like it's not going to take that much time to learn everything. But it might be the case that I'm just not aware of the things that I don't know yet. And that's the thing that I'm trying to think. Like figuring out what questions to ask that I might not be asking to reach to the next level.
Alrighty, Hosses, welcome back, and in this video I want to talk to you about structs. Now, what the heck is a struct in Python?
I guess maybe the next level is not on Python itself, it's programming in general. So it might be the case that is different in that way. That in the gyms is only one thing, but programming, since it's a lot bigger, the beginner phase is just learning these languages, and the advanced phase is not learning the languages, but learning the infrastructure itself. So it's not actually learning new methods of the languages, but learning assembly and C++. And these things, then you become really advanced, because then you start understanding how the computer thinks from the bottom. So that might be the best path.
Well, a struct is a way that you can actually take any type of data in Python, whether it's numbers, letters, strings, whatever, and you can convert it to bytes format. So, first question is, why would we ever want to do this? I mean, it might be interesting to know how your computer stores memory or how it transfers data over the network, but we really don't care about those ones and zeros most of the time. So why are we learning this? Well, I'm actually going to be making a new tutorial series about some network applications in Python, and whenever you work with network applications, you actually need to read the bytes value. So you're on a network and you see all these ones and zeros coming across, and you need to actually interpret it, because humans can't read ones and zeros, so we need to figure out a way to take all of that data, that raw data, and turn it into something that's readable for humans. So that's why I'm going to be showing you how to use structs, basically to turn ones and zeros into something that humans can read. So the first thing that you need to do is go from struct import all. And I'll show you guys how to pack and unpack and what all that means. So the first thing I'm going to do is we're going to have some data, and I'll just have like 3 numbers, like 6, whatever, 19, and some float, and we'll store it as bytes. So store as bytes data. And someone is texting me. Actually, that's mail. And it was an update for my Facebook page. All right. So how do we take data and actually convert it to bytes? Why would we want to do this? Well, say we're preparing to send some data across the network. Well, let's go ahead and make a variable, and I'll just name it pack data. And what you need to do is you need to call a function called pack. Now, as you can see before I hit enter, this is going to take 2 parameters. The first one is the format, and the second one is going to be a list of values. And it can either be just one value, like a number or a letter, or it can be, a list like, 10 different numbers. So remember, format and values. All right. So if you go to the Python documentation, they'll say that what you store, and they'll give you the letter for what it is. But say that we wanted to store 2 integers and a float, some decimal point. Well, the key letter for integers is I. So if we wanted to store 2 of them, just type I twice, and then I'm also going to store a decimal point or float. So I'm just going to write that. Now, if I just want to store 5 integers, then I'll just write I 5 times. Well, let's go ahead and store 2 integers and a float. So now with the comma separated this, we just need to give it 2 integers and a float. So I'll say like 6, 19, and a float like 4.73. Whatever. And of course, if you're using like strings or characters or anything like that, then this is going to be different. But basically, whenever you have data such as this, and you want to convert it to a byte format, just write what type of data you're storing, and then the data itself. Simple enough. Now, if you actually just want to see this right now, we can print it out. And remember, whenever I print this out, it's going to print it out in byte format.
It's kind of hard to read there, but he typed IIF for integer, float.
So this B right here, it signifies bytes, and now you see all of that stuff. So /x06/x00, all of that crap. So again, whenever you transfer data over the network, that's what's actually being sent. So that's why when a lot of people try to build like password sniffers and they start seeing all that, they're like, what the heck? So now we know what's going on behind the scenes. Now I want to show you guys some other cool things before I show you guys how to take that byte data and actually convert it back into human readable form. So this is going to come in handy later whenever we're learning about why we need to get a certain amount of bytes. So check this out. This calc size, this is a built-in function that just tells you how many bytes are needed to store some value. So let me just type I right there, and let me just type something like F and IIF. IIF. All right, so check this out. So we print out the byte data. We already saw that before. And now I'm going to print out the size needed to store an integer, a float, and our data, which was 2 integers and a float. All right, so it says 4, 4, 12. So whenever you're sending data across the network, and you're sending an integer, it takes up 4 bytes. That's how much space or memory it takes up. Same thing with a float. They're the same size, 4 bytes each. And whenever we try to calculate the size needed to store 2 integers in a float, it was 12. And that makes sense. 4 plus 4 plus 4 equals 12. So later on, what we're going to be doing is we're going to say get the first 12 bytes of this packet or something. And now you guys are like, oh, so that's why, because, you know, that's how much space it takes up. So easy, breezy, beautiful cover girl already. Now we need to figure out how to get this data, all this byte data, and convert it back into human readable form. Well, if pack was the function to make it byte data, unpack is the function to get it back to normal. So I'll say to get, I don't know, data back to normal. Say to get byte data. All right, so I'll just name it original data, and what we need to do is we need to unpack it. Now, whenever you unpack it, you also need to give it the format. So it's going to be looking at a bunch of bytes, which is actually this thing, and it's going to say, okay, what do you want me to do? Like, are there integers in here? Are there characters? Are there strings? Are there floats? How do you want me to unpack it? And we said that there's actually 2 integers and a float in here. Now, as a second parameter, you just give it that pack data right like that, and this is all your bytes data. So now whenever you run this, and we need to actually print it out, then check it out. All right, so all this was from before, and now we unpacked it, and we got 6, 19, and our float, which is 4.73, and some numbers on the end because computers are awesome at storing decimal points, but we got a little extra values right there. So there you go. So another thing that I actually want to show you guys is this. If I just copy all of this byte data right here, remember, this is basically 6, 19, and 4.73 stored as bytes. You can actually just do this. Print, unpack, IIF, and put all your byte data right there. So this may be a little bit easier to visually see whenever you first start learning about this. So let me go ahead and run this, and we get the same results right there because, of course, this variable is equal to this right there. But basically, whenever you have to work with bytes, or you need to have byte data and transfer it back into human readable form, then you can use pack and unpack from struct. So pretty easy stuff. There you go. I'll see you guys next time.
Stream more and
Hello
move
friends
on.
and welcome to PyShine Learning Series. This video is about the Python built-in module named struct. This module performs conversions between Python values and C structs represented as Python bytes objects. It uses format strings as compact descriptions of the layout of the C structs. We can use struct.pack function to convert a Python data into bytes of various sizes. The byte size depends on the format value. The Python data such as text, audio and video can be sent over the network socket. For example, if we want to send a digit 1 from a client to a server, we should pack it in the client and then send it to the server. At the server, we can recover the Python data by unpacking the bytes data. There are various format types. In this example, we have used 2 bytes by using the letter H. As you can see, the digit 1 is converted to 2 bytes in the packing. In the unpacking, we use the same letter H as the format type to recover the same digit 1. This table shows a variety of formats we can use. The small letter are mainly used to indicate signed C types. On the other hand, mostly unsigned C types are indicated by the capital letters. As an example, we pack the digit 1 using the letter B, which takes 1 byte. We can also pack the digit 1 using the letter H, which takes 2 bytes. In case we need to send a string like ABC, we should use B before the string and use the letter S. The letter S indicate 1 byte, and appending a digit to it will increase the byte size by that times. So by using 3S we can pack the ABC. If we only write letter S, then the pack. A live webcam video, please give a thumbs up, share and subscribe.
And I'm doing this video.
Welcome. In this tutorial, we are going to learn about struct module, which enables conversion between any Python object and its equivalent C struct representation as a byte object. So earlier we saw string object, which is having encode method. It is used for converting string object into the bytes object, and bytes object can be stored to the disk or it can be transmitted over the network. So same way, struct module we can use to convert any Python object to its equivalent C struct representation or into the bytes object, and that byte object can be used to store that particular Python object to the disk or it can be transmitted. And if you're transmitting over network, the same C struct representation of byte object can be used to convert that byte object into the Python object. It supports objects that support buffer protocol and provide either read-only or read-writable buffer. So built-in objects such as bytes and byte array implements buffer protocol. So that can be used to store the result of conversion of a C struct, and it can be also converted the C struct representation into the Python object. So let's begin with the format. So format of a struct is represented in a string. So first character of given format is determined as a byte order. So we can use any of the given character to represent the byte order. If the first character is not byte order character, it is implicitly taken as a native. In this case, it is @. And for native byte order, padding is not added at the beginning or at the end of a encoded struct. Padding is only added between the elements of a struct. And for non-native bytes, such as little indent or big indent, no padding is added between element. And for alignment and with the size of a struct given, zeros are added to the end of the struct. We will see this with example. And for format of a struct, which is specified in the string, use standard size and alignment if you want to convert in a platform independent manner. Okay. So these are the format characters which can be used for representing Python data type into C type. These are the Python data type and their equivalent C type which can be represented in the format. Small n and capital N are available for only native byte ordering, and P is for Pascal string, a short variable length string stored in a fixed number of bytes. A question mark is format character which returns value either true or false, which is boolean. We can use any of the character to represent single type of object which to be packed or unpacked inside the string. Here we can write 4 times I, which means when we are packing or unpacking, the order of element will be only 4 elements and all of them will having type of integer. Instead of writing repeatedly I 4 times, we can use short denotation for 4 and I, which is equivalent to this. Same as for format character S, the length of string is represented as number preceding the type of data. So 10s means 10 bytes string. And if you are not providing any number preceding to the given type, it will take implicitly length as 1. And you can leave space between 2 types. So if we are formatting like this, first 5 integer. First function of struct module is calculate size. So for given format, returns the size of struct format. So here in calculate size, we are providing first is I, which means first element is integer, then 13 bytes of string, and F is for float. Same we can check inside the table given. And it will return the calculated size of a given structure. So if you execute it, it returns the size in bytes, first integer, and after 13 bytes. Here we can see at the end of struct class, which takes only one argument, format string, as we have explained here. So first character of format is the byte order, which can be any of this, and preceding by the format character, which defines the structure of given struct class. So it returns the new struct object, which can be used to pack or unpack data according to the given format as a string. It has 2 attributes. First one is a format, which returns the original format string, which is passed in the constructor of struct class, and second one is a size, which returns the calculated size of a struct, which is equivalent to this method calculate size of a struct module. So let's construct the object of a struct class. Here we are providing first character is a byte order. Here we are explicitly specifying native byte order. After that, first character is I, which means first element is integer, followed by 13 bytes string and float. And if we execute it, their attribute format and size. Here we can see format is same string passed to the constructor and the size of a given format. Next, we will see the function of a class or struct object. First one is pack, which will return byte object from the given elements, takes variable amounts of positional argument. So from the given Python objects, it will return bytes object, which is packed in given format. So we have constructed struct object in certain format. In same format, we need to pass Python object. So here we have declared first element must be integer, followed by 13 bytes of string. So it can be at most it can have length of 13 bytes, followed by float. So 3 elements here, which can also be represented as separated by case. So if you execute it and if we pack it, it will return bytes object, which is equivalent of structure of given format this. Now this byte object can be stored directly to the disk or it can be transmitted over the network. Now we will explore all the byte order and we will see how they are or encoding the given order of Python object into their bytes representation. So for each representation of byte order, we are creating struct object with format. So same format is same, only byte order is different. And we will pack the same items using different byte order. So here we can see first one is the default formatting in which we are not specifying any byte order. So as explained earlier, it will implicitly take as a native byte order. And if we provide explicitly native byte order, which will result in same. So here is the explicitly specified native byte order and their bytes representation, which is exactly equivalent to explicitly defined native order. Next one is a little indent, and last one is a big indent, which will pad in the beginning. And little indent, as you can see, it is padding in between the elements. Next method is pack into, which take 2 mandatory arguments, buffer and offset. So it will pack the result of given formatted packing into the given buffer object. So buffer object can be any object which supports buffer protocol. So earlier we saw bytes and byte array. We can provide any of that object here. Next is an offset. Offset at which we want to insert position or the index at which we want to insert the result of packing, and followed by the variable amounts of positional argument which specified ordered Python object in given struct format. So here we will pack given Python objects into the byte array. So first we will construct the struct object in same format as we saw earlier in native byte ordering, and we will construct byte array of 56 bytes. Earlier we calculated the size of struct. So if we print struct1 size, it is storing as a 24. So when we are storing the next element, we must increment the offset by 24. So based on the size of a given structure, we will progress into the byte array. So here we are packing more than one object into the buffer. So earlier we used pack method, which only return byte object from one sequence of given format. It cannot handle multiple sequence of formatted Python object. So if we have multiple sequence of given formatted Python object, we have to use pack into method. So we can use same format and different Python object to struct or pack Python object into the same buffer. So here first we are storing this object in the beginning of buffer, and we know it will take size of 24 bytes. So from 0 to 23 index, it will store result of this pack, and from beginning from 24 index, it will store result of this pack. So if we execute and print the buffer, it will print the result of pack into. So this is the content of byte array, which is holding 6 Python object, and if we break it into according to the given format, it is holding 2 struct value in this format. Next method is unpack. Takes one argument buffer and returns tuple object containing unpack value from the buffer using struct object format. So we have same format, we have constructed struct object, and we have now buffer as a bytes object. So same as we constructed from pack method, the result of byte object, same object we will provide into the unpack method, which will return tuple object of original Python objects. we execute it, it is returning. First one is integer object, second one is a string object represented as a byte, and third one is a float object. Next function is unpack from. It takes two argument buffer and offset. It works same as unpack, but it will take buffer and we can provide offset. From offset, the length of given format, it will extract only that length of buffer and unpack from that buffer content. So earlier we used pack into method to pack more than two sequence of Python object according to the given struct format. So we have multiple struct element here. We want to unpack the second struct format, which is beginning from index 24. So we can use unpack from method, which takes offset as an argument. So here we will provide 24. So it will begin unpacking from index 24, and length of the size will be size of the given format. So it will also read 24 element in given struct format. Values here. Okay.
Gotta get it.
Hey everybody, it's Brian. Welcome.
I think for now the use for me is gonna be just so identifying other people's code. But maybe I will use it in the future. If that's the case, I'll probably revisit a couple of times to understand. It doesn't seem like it's something that I might use right away.
Welcome to the 17th.
I'm gonna watch this video and then I'm gonna be done for now.
Python tutorial. It kind of screwed me up my notes, or we smushed the last two together into one video. So it kind of screwed me up a little bit here. But today, we're going to be talking about binary files and structures. And to kind of help me with that, we're going to look up on Wikipedia the JPEG file format. You're all familiar with pictures. I don't even know this cute cat. Everybody knows I love cats. So what really makes this file? I mean, how do we get that image on the screen? Well, you use what's called a structure. And I use JPEG on purpose because it's a very complex data structure. And if you just kind of scroll down here, you don't have to read all this, but just understand. Remember how we talked about, hex FF is 255 in the last tutorial? That's the start of the image. So you have this nice structure here to work with. This is the common MPEG marker. And what this is just simply a data structure. You'll hear this in different languages. You'll hear it called a header, a structure. In Python, they're just structs. But they're very easy to work with in Python, and they're very painful to work with in some other languages. Now, what would you use a struct for? You can see how this just denotes something. It's like the size, the progressive, whether it's got Huffman tables, quantization tables, define restart intervals, scans. I don't expect you to know any of this. What I'm getting at here is JPEGs are actually very complex. You'll have this 8x8 subimage. That's right, subimage, meaning a picture can actually be made up of other pictures. And those are structures that are read. You got it from a binary file. Now you start to understand a little bit more about why binary files exist. You can pack a lot of data into them. I almost say like 10 times the amount of data you put in a simple text file if you try to describe something. And you can have these beautiful structures, which are very easy to work with. So we're going to actually not mess around with images because it's a little too complex for us right now. But we're going to make our own structure. So let's actually go in here, go new. Did I call it video 18? I did. This is video 17. My bad. Like I said, my notes just totally video 17. There we go. I'm going to call this struct. Now, first thing we want to do is I'm going to put a link in there for when you download my tutorial off my website that you can very quickly go out and read about this. But we're going to from struct import star. What that's really doing is we're taking the struct and we're importing everything inside of it, that struct package. We've done this before. And we're going to make a string literal here, which is, of course, the path to our file. And yours will be whatever, see my documents, etc., etc. Little quick rant. It just bothers me. I mean, I used to love Windows, and I got a Mac, and I got into Linux, and it just bothers me that Windows is different than everything else on the planet. It's like, why can't everything just be the same? So, with a structure, we need a format. What does that mean? It means you need to understand what you're putting into that structure. You don't just willy-nilly start throwing bits in there. I mean, crazy things will happen, right? So with a structure, you have two concepts, packed and unpacked. Pack is when you're packing it down to store it into a file, or like into a box. Think of it that way. You're going to package it. And unpack, well, you guessed it, you're pulling it back out of that file, and you're going to do something with it. So I'm going to say packed equals pack, and this is from the struct package. Now, first thing you need is the format. Then you need some data. You notice how there's a star there, star values. What that means is it accepts one or more. We can just go infinity and beyond. So if you ever see star values or star something, you know that you can have multiple in there. So we're just going to say 1, 2, 3, why not 3.14? So that's our structure. Integer, integer, decimal. That's how that reads. So integer, integer, decimal. That way, the struct package, particularly this pack function, knows exactly what we're storing. We're giving it a format to work with. If we give it the incorrect format, it's going to start squawking, you're going to get all sorts of errors, and it's going to get ugly. This is a pretty dumbed down example of struct pack. You can find some very complex examples out on the internet, but I really wanted to dumb it down just so we understand what's going on here. Now, we've got our packed structure here. So let's just print this out just to see what it looks like. I'm a big fan of show and tell. And you can see there's our structure here. Holy moly, look at that. That is a whole lot. What's going on there? Well, if you paid attention during your computer class, you know that into binary write as out. And we're going to say f.write bytes, because we need to convert this into, you guessed it, bytes pack. And what that does is it takes our binary string and converts it into, you guessed it, bytes, and then writes it down to the disk. Now we're going to print, reading the file. Whoopsie. There we go, reading the file. We're going to say with, open, out. But I'll be gone for structure. You would actually say only read a.
Okay, I think I'm done for now. I might come back later today. And if not, probably tomorrow. And if not tomorrow, it's gonna be Christmas, so I'm not sure if I'm gonna stream or not. Not sure what's gonna happen, but yeah. Next time I come back, I'm gonna study these things here. after I'm done with these 5 topics here, I'm gonna open the Cs file and study the Cs module, and I'm probably gonna read the Python documentation. And once I feel like I have a good understanding, I might try to play around with that script again to change the way that the graph is made. Yeah, so I'll get back later. See ya.